All right, so first speaker here is going to be Chris Porter, right, with a host of collaborators on Decker attack surface reduction via on-demand code mapping. And Chris is a doctoral candidate at Georgia Tech, and I apologize, I did not have his little bio. It didn't show up here magically. So, but either way, thank you so much, Chris. Go ahead.
Yeah, thank you. Hi, everyone. Yes, I'm Chris Porter, and my collaborators are Sharjeel and Santosh Pande. I'm presenting our work Decker, attack surface reduction via on-demand code mapping. So software continues to be susceptible to existing and novel code reuse attacks. Code reuse attacks are a problem that we want to solve. These are software attacks that leverage existing code and programs to perform some malicious action. They're commonly built today with what are called gadgets. Gadgets are short sequences of instructions that can be stitched together to form gadget chains. It's the gadget chain that carries out some malicious behavior. If you've never heard of gadgets or gadget chains, it's no problem. Let's run through a quick example of one technique called return-oriented programming, or ROP for short. Right here, you're looking at a few ROP gadgets scattered throughout the code section of a program. And we have an attack payload. In this case, it's in the stack. So the top of the stack is the address of our first gadget. It'll get kicked off when the program executes a return. And at that point, the ROP chain is in motion. We have a green stack pointer, and our instruction pointer, a little grasshopper, is at the first gadget. We execute the first gadget, a pop from the stack in this case, and now we're at our first return statement. So we execute the return, which just pops from the stack and jumps, by design, of our stack payload to the next gadget. And this gadget happens to be another pop from the stack, and we get to our second return. The return pops from the stack and jumps to the third gadget, a move instruction. We execute the move instruction, we get to the third return statement, and so on and so forth. And this continues until you execute a string of gadgets, which together amount to a malicious action, like spawning a shell on a system. So refer to our paper for a real-world example, but to summarize, all gadget chains, no matter how simple, fundamentally work like I showed. They leverage pre-existing snippets of code and move from one to the next to propagate the attack. And we know that software is bloated with unused code, and we know that this unneeded code contains gadgets, so why not remove it? Debloating is a proposed defense against code reuse attacks. Debloating as a defense technique has become relatively popular in the last couple of years, but there's shortcomings with current approaches. In general, they tend to be too conservative, which leaves too much code available, or they compromise soundness by specializing the application for only certain inputs or features, which can lead to crashes or incorrect output. Now, before continuing, two definitions will help. We talk about sound transformations in our work. By sound transformation, we mean a program transformation that does not change the semantics of a program. Program transformation that induce crashes or cause incorrect output are unsound. And may use code is code that may be used by the program under certain input or execution conditions. You could also say it's code that may not be used too. It's just code that depends on input and dynamic context as to whether or not it'll execute. Now, this is a table of several properties of popular debloating frameworks: Piecewise, Chisel, Razor, and Blanket. You'll notice some are geared towards libraries, other towards applications, some need training input, etc. The last two rows, whether the technique is sound and whether it can debloat may use code, are critical in our view. You'll notice only Piecewise and Blanket are sound techniques. Programs debloated with Chisel and Razor can actually produce bad output or crash, which limits them from practical adoption. Furthermore, only Blanket can debloat may use code. The ability to debloat may use code is critical for higher attack surface reduction. Now, even though Blanket achieves both soundness and the ability to debloat may use code, Blanket does not work on applications, only libraries. So with that in mind, we're motivated to tackle application code. To the best of our knowledge, there's no general technique today that works on applications as a whole instead of libraries, is sound, and can effectively debloat may use code using dynamic context. We present Decker. We embrace this kind of oxymoron that Decker reduces attack surfaces with constructive techniques. We use the terminology of a deck to describe the active sections of code that the program effectively stands on, and when a deck is unneeded, it can be removed. The way we're going to do this is by mapping only code that is currently needed by a running program, and we'll disable all other code so accesses trigger a runtime exception. This is all at the granularity of system code pages, and Decker consists of both a compiler and runtime component. Our threat model for Decker is similar to related work such as Razor, Chisel, Blanket. There are more details in the paper, but I want to highlight a couple things. First, our focus is on attack surface reduction. We assume the attacker can initiate and propagate the attack. And second, the integrity of indirect call targets is out of scope. If you're familiar with orthogonal techniques like CFI or CPI, then you'll know they're designed specifically to tackle that exact problem. All right, let's walk through an example to see how Decker actually works. This is a deck. And in our analogy, this is an example program standing on the deck. All code on the deck is always executable and available for attack. Now consider the associated pseudocode for this example call graph. Function main may invoke foo and bar. And the idea of Decker is to construct decks only for code that is actively being used. So when this program begins executing, only function main is active. So Decker constructs a deck solely from main. If execution reaches the call site of foo, then we create a deck for foo, which maps its code as executable. The program can continue normally to foo, and when foo returns, the deck is torn down. The call to bar is handled similarly. At its call site, we construct its deck, execution will flow into it, and upon return, the deck will be torn down. As you can see, just before the execution of a function, the code is activated, and after it completes, it's deactivated. The code area available to an attacker is therefore limited only to active functions. Now, a normal program keeps all of its code always active. For the sake of argument, assume in this example that there's 3 gadgets, one in each of the functions. Assume also that these 3 gadgets are sufficient for creating a gadget chain. Now, under these assumptions, a gadget chain is feasible in an unprotected program. In contrast, Decker does not allow this chain. The strength of Decker is its ability to remove large sections of the program that are not in use. For example, when only main is active, 2 of the gadgets are removed by Decker, so this gadget chain is infeasible. Similarly, in this scenario, foo is activated but not bar. And lastly, here bar is activated but not foo. So under none of the scenarios will gadgets in foo and bar be simultaneously active, hence the gadget chain is infeasible. And as we will show in the evaluation, this approach is effective in practice in undercutting gadget chains. All right, let's get into some of the details about how we construct the decks. So Decker's approach is largely based around program structure. What I mean by that is because it is an instrumentation technique, we have to be very careful about where we instrument the program. Loops in particular are problematic. If we instrument inside of a loop, then the instruction will be repeatedly invoked, which kills performance. Our analysis led us to consider 4 types of decks, which we'll illustrate by way of another example. So here's a slightly more complex call graph than we just looked at, along with its associated pseudocode. You'll notice main calls A and B. Notice also that B is called within a while loop. We can also see that A calls B, and A also invokes a function pointer. And B calls C. All right, now let's walk through the 4 deck types. So the first deck type is called a single deck. It occurs in a non-loop region. The call from main to A is an example. Only the callee needs to be mapped executable. The second is a loop deck. It occurs at the entrance to interprocedurally outermost loops. The while loop in main is an example. Both B and C need to be mapped executable at the loop entrance. This avoids any further instrumentation inside of the loop. The third is a reachable deck. It occurs at the entrance to a loop region via a non-loop region. So the call from A to B is an example. As we just saw, B is within a loop region, and to avoid overheads, we cannot instrument inside of this region. So when we enter this region from A, we must map all statically reachable functions from B, which includes C. Now the last is the indirect deck. Now it occurs at indirect function calls, and the call from A to func pointer is an example. We rarely know the unique function target at build time though, so what do we map here? Well, we know that static function pointer analysis can produce a set of targets for function pointers, but it's almost always an over-approximation. In debloating terms, that over-approximation means we're going to have limited attack surface reduction. So instead, in Decker, we resolve this problem at runtime. We pass the function pointer to the Decker runtime, and the Decker runtime finds the associated function and maps any appropriate pages. And one last point about indirect decks, it forces us to violate the rule of thumb and instrument inside of loops. Now, after deck instrumentation, there's a linking step. I'll refer you to the paper for details. In brief, however, the problem we need to solve is that functions in one deck can occupy the same code page as functions in another deck, and we do not want to inadvertently include gadgets from other functions when we map code pages as active. So the solution is to separate the functions in our deck sets into disjoint sets and use a linker script to force these disjoint sets into separate code pages. Now there's 3 goals in our evaluation. First, we want to know the performance slowdown due to Decker. Second, we want to know Decker's effect on total gadget reduction. And lastly, we want to know whether Decker can actually break real gadget chains and thwart attacks, including jump-oriented programming attacks in Windows. I'll summarize our results. For performance, Decker achieves about 5% average overhead or better for Spec CPU 2017, GNU Core Utils, and Nginx. In terms of security, Decker removes about 70 to 87% of the total gadgets on average across these same applications. And crucially, it does this without compromising soundness. And lastly, breaking real-world gadget chains is an unexplored metric that we emphasize in our evaluation. And Decker indeed breaks gadget chains. It breaks a syscall launching ROP chain across all applications, and our analysis details how it removes critical functionality from job chains in our Nginx study. I'd love to share more evaluation details, but due to time, I'll just refer you to the paper if you're interested. We can, of course, discuss offline as well. And with that, I'd like to conclude. So in this work, we presented Decker, an attack surface reduction technique for applications that's sound and enables may-use code on demand. It requires zero training, user inputs, or specifications. Its total gadget reductions are in line with and often beat prior art. Its runtime overhead across all applications that we studied is, on average, about 5% or less. Decker breaks the syscall ROP chain over all possible DEC sets that we logged. And there's strong evidence that useful job chains are substantially hampered or impossible to build for both Linux and Windows when using Decker. So thank you. We have an artifact. You can find the link to it in our paper. And with that, I'd like to hear any comments or questions. Thanks again.